All right, we're going to start our next session. If Neal is still awake, he is.
Yeah,
For people who have been awaiting the packet drill impatiently, here we go. So take it away, Neal, whenever you're ready.
great. Thank you so much. Um, all right, great. So yeah, today I'm going to talk about using Packetdrill, which is sort of a power tool for automated testing of the Linux networking stack. Let's see, make sure this switching slides works. Yeah, I wanted to start off with a few acknowledgments. I originally wrote the Packetdrill tool back in 2011, 2012, but since then it's been a real collaborative effort across many people, both in the Linux networking team at Google and also in the wider Linux community with contributions from BSD and IETF folks as well. So thank you all for your contributions both to the tool and the test suite. And without further ado, let's dive in. So just a quick outline of the things I wanted to talk about today. And also, if there are quick clarifying questions, I guess feel free to jump in. But there's a lot of material, so maybe we can try to save big questions for the end. And I'm happy to take questions in the chat afterwards, and of course on the mailing list as well. So I'm going to talk about Packetdrill, what it is, what it's trying to do, what it's good for, talk a lot about the scripting language and how you can use it to write and run tests. I'll talk about the design and implementation of the two modes that you can use it in. I'll talk about varieties of Packetdrill out there, how to download and build it, troubleshooting tests when they fail, some recommendations for best practices. I'll talk about some ways you can integrate Packetdrill into your development workflow, talk about how to submit patches, talk about some details of protocol support for various nooks and crannies of TCP/IP, and talk about various tips and tricks with some concluding remarks at the end. All right, so let's dive into a sort of quick introduction to Packetdrill. So what is it? So I think of Packetdrill as basically a scripting tool for unit testing network stacks. And this means the entire TCP, UDP, IPv4, and IPv6 networking stack of a sort of Unix-style operating system, from the system call layer all the way down to the NIC hardware if you want to. And it works on Linux, FreeBSD, OpenBSD, NetBSD. There are ports for Mac OS. And it basically has two different execution models you can use for testing network stacks. So the first is sort of a simple and easy and quick one. It's local mode, where you're doing testing within a single machine and you're using a ton virtual network device. And this makes things faster and easier. And then the second way is remote execution. And with this approach, you're testing over a real physical NIC on a real physical LAN. And this is good if you want to do detailed testing of real drivers or real NICs. And overall, Packetdrill enables some quick, precise, packet header level tests that are reproducible and automated. It's been open source since 2013, same license as the Linux kernel, GPL v2. And it's designed to be interpreted for fast test and edit cycles, even on production machines that you might have that might not have your regular build environment with GCC and all that. So that's sort of the quick overview. When is it useful? The main ways that we find that it's useful are number one, if you are doing kernel networking development and you want to test a new change or bug fix or a new feature, it can be really useful to have this as a tool for black box unit testing to make sure that your logic that you are changing or adding is doing exactly what you expect when you get a particular packet or a particular system call. Second, it's good for automated regression testing to catch bugs that other people might check in over time. And third, it can be good for troubleshooting. If somebody reports a bug and maybe they have a TCP dump PCAP trace, and you want to reproduce that issue using that trace, or if somebody reports the generic symptoms of a bug and you have a theory about what particular combination of system calls and packets might result in that buggy behavior, you can test that theory quickly with Packetdrill. So what aspects of networking stacks can it test? It can test correctness, meaning does your protocol implement the specification? It can test reliability. Is the implementation handling challenging corner cases well? It can handle interoperability. Does it handle the kind of packets that other stacks might send your stack? It can handle some kinds of performance. So particularly it's good for asking whether congestion control or loss recovery algorithms are correct, even in tricky cases. And finally, it can be used for security testing as well, in terms of testing how a protocol stack handles malicious messages that might have weird header values. When is Packetdrill less useful? There are a couple common types of testing that people do and people need, for which Packetdrill is not really a good fit. The main ones that come to mind are, first, if you're doing high-speed or long-duration performance testing, where you want to test CPU usage or throughput or latency, it's not really a good fit for that. Instead, you should use something like Nepr or NetPerf or the various iPerf flavors. If you're doing testing of protocols above layer 4, like HTTP, things like that, instead, you should probably use a load testing tool. And if you're doing fuzzing, you should probably use syscaller, which is perfectly suited to that and can do network testing. So let's dive into the Packetdrill scripting language. And let's start with the design goals. What are we trying to achieve here? So first, we wanted this to be interpreted so that you can have fast edit and test cycles. You don't need to run make or compile things, link things, copy binaries around. And you can, this means also that you can run Packetdrill on a production machine that might not have your compiler or your linker, etc. We wanted it to be easy for reading and writing scripts for folks who are doing the actual kernel network stack development. So that means this is a population like us who are used to reading and writing C code, used to looking at strace dumps to understand how an application is interacting with the kernel, used to looking at TCP dump packet traces to understand a protocol's behavior on the wire. And then I wanted it to be feasible to turn small strace or TCP dump traces that you might encounter in production. I wanted to be able to turn those into test cases. And finally, I wanted to encourage really simple, succinct tests where we want to encourage each script to be sort of simple, easy to write, easy to read. And it should be a description of one simple scenario, not a complicated thing. And as a result, it intentionally does not have conditionals or loops or variables to try to keep things simple. So let's go through the design elements of the scripting language. So really, it just has these 5 simple elements: comments, system calls, packets, shell commands, and Python scripts. And we'll go through each of those in turn. So starting with the easy and obvious one, comments. Obviously, these are for documenting what you're trying to accomplish in the test. For humans who are reading or maintaining the code or trying to understand a test failure, Packetdrill supports both C and C++ comment syntax. So system calls. Packetdrill allows you to specify system calls by using a syntax that's borrowed as much as possible from strace, where you specify the system call to invoke, and then you specify the output and return value you expect. And these can be blocking or non-blocking system calls, although it can only handle one blocking, sorry, that's a typo there, one blocking system call at a time. And the syntax is familiar to anyone who's ever looked at strace output. It basically looks like a system call as represented here. So packets. Packetdrill also allows you to specify the exact packets in a test scenario using a TCP dump-like syntax. There are sort of 2 different kinds of packets. One is an inbound packet that your script is specifying that Packetdrill should construct and then inject into the network stack under test. And then the second type is an outbound packet that your script is expecting that the network stack should be sending, and Packetdrill will sniff for that packet and then verify that it has the timing and contents that the script was expecting. And this applies for TCP, UDP, ICMP. And then there are some examples here of the syntax for specifying a packet. Here's an example inbound packet where the script wants to inject a SYN packet into the kernel under test. And then an example outbound packet where it's specifying that the script is expecting the kernel to send a SYNAC packet. And as you can see, the notation is very close to tspeedo. The next piece of the puzzle here is shell commands, which allow you to have a piece of your test that configures or inspects the machine under test using regular shell commands, arbitrary shell commands. So often a test will use the IP binary or sysctl. TC can use echo to echo values into device or module parameters. And the syntax is just simple backtick single quotes with the shell command inside there. And then the next element of the language is Python scripts. And these are generally used to give you some flexibility so that you can check or print internal socket state. What happens here is that Packetdrill will, when you insert a Python script in the middle of a test, Packetdrill will implicitly call TCP info, TCP CC info, and SOMEM info for you to grab all of those state variables, and then it will save those away. And then at the end of the test, it will run the Python code using the values that it grabbed using those system calls. And then that allows you to basically enclose some Python in these little curly braces. And you can use multi-line scripts that make assertions. They can even define and call Python functions. They can print output, whatever you find useful to either examine or make assertions about what the kernel or networking stack is doing. So here's an example. Here we're asserting that the congestion window was 7 packets at that point in the script. So a key part of Packetdrill is that it's a script of what happens over time. And that means that every event in a Packetdrill script starts with a time specifier that basically tells Packetdrill when should this event happen. And there's a fair amount of flexibility in the way that you can specify these timing, the timing of these events. There are a couple different models here. You can use absolute times, where you're saying that a particular event should happen at a particular offset since test start. Or you can use relative times, where you're specifying the time at which the event should happen relative to the execution of the previous event. You can specify time ranges that are absolute or relative. And you can also use wildcard times, where you can say, I don't really care what time this event happens, I just want it to happen. And then the way the Packetdrill checks time is that it tries to check whether, well, for events that the tool itself is doing, it uses that specification to decide when to trigger that event. And for events like outbound packets, where it's checking the behavior of the system under test, it basically checks to see whether the event happened at the expected time. And when an event happens at an unexpected time, Packetdrill raises a test failure. Now, of course, often things can happen at a slightly different time than what you expect based on CPU or timer variations. And so to avoid flakes, there is a specified tolerance for timing variation. And the default is 4 milliseconds, which is a fair amount of variation that it's tolerating while still being able to check most loss recovery and congestion control behaviors. But if you need a different level of tolerance, then you can use the command line option to set that. And that can be really useful for kernels that are built with in debug mode or with address sanitizer enabled. Of course, those kernels are slower, so things can take longer than you expect. And finally, there's also the fact that for system calls that block for a while, you want to specify how long they block. And so Packetdrill supports that syntax with the start and then ... and then the end time. So there's also a feature in the language where you can specify 2 special optional commands, one for setup at the beginning of a test and one for cleanup at the end of a test. And these are special in that, first, if they're specified, they're always run, even if a test fails. And they don't have a time specifier. Their time is implicit in the fact that they are at the start and end of the test, respectively. And also their execution is not timed. So they're ideal for inserting a lot of setup or a lot of teardown code that might be slow and where you don't care about the performance of that code. And the setup code is generally useful for setting up initial host or namespace configuration using IP or TC, sysctl, etc. And cleanup is intended to allow you to check behavior and then clean up any changes that you may have made at the initial part of your test or over the course of your test. And that one is useful because it always runs at test conclusion, even if your test fails somewhere in the middle. So it's a bit like a destructor or a try, catch, finally block, where you want to make sure that you always execute this cleanup code at the end. So another useful aspect of the scripting language is that it has an ellipsis construct, ... which basically means in several different contexts that I, as a test developer, I don't really care about this detail, just make it work. And it sort of tells Packetdrill to just fill in the boring boilerplate kind of in the expected way, just to make the test work. And it can be handy for several reasons. First, it makes it easier to write tests because you don't have to choose the boring details for IP addresses or the contents of test buffers. Second, it eases the reading of tests. You don't have to read the boring details. And then finally, it allows scripts to be generic so that they can be reused by being agnostic about details that can vary between IPv4 and IPv6. Speaking of which, Packetdrill does support 3 IP address family modes. The first is it can run a test in IPv4 mode, and that means the sockets that it creates are AF-INET, and then the IP addresses on virtual devices or real devices or in packets, those are all IPv4. Similarly, IPv6 mode is using AF-INET 6 sockets, and obviously IPv6 addresses in packets and devices. And then finally, the more interesting one is IPv4 mapped IPv6, where the socket is AF-INET 6, but you've got IPv4 packets and addresses. And these days, most production quality software is written using this final approach, where you have an AF-INET 6 socket, which can accept either IPv4 or IPv6 connections coming in. So that's an important case to test as well. And you can pick your mode on the command line via an IP version flag, and you just specify which approach you want to take. And then we consider it sort of best practice to make test scripts as much as possible be able to be run in all 3 modes using that ellipsis construct that we were talking about. So you basically want to, as much as possible, take all of the address family specific parts that you might have in a sequence of system calls and just use the ... feature to elide out the aspects that are address family dependent. In that way, this code snippet here can be run in any of these modes, and your test infrastructure will generally run a given script using all 3 modes. And there is a test orchestrator with the Packetdrill distribution that does just that. So putting it all together, on the next slide, I'm going to show an example of a Packetdrill script that's doing a very typical kind of thing that you might test with Packetdrill, where we're going to test loss recovery, specifically fast recovery, and we're going to test congestion control, specifically cubic, and make sure these core aspects of TCP behavior are working as expected. So here's the key up at the top, where in black we have system calls and also commands, I guess. In blue, we have incoming injected packets. In red, outgoing sniffed packets. And in green, we have Python scripts to make assertions about what's happening. So at the top, you can see here we have a setup command that is putting the machine into the state that we're expecting for this test, because we are explicitly testing cubic in this case. So we want to make that dependency explicit and make sure that the test has the environment it expects. And then we do the sort of typical server-side connection setup in this case, where we create a socket, bind and listen, and then we inject a SYN packet. Packetdrill will inject that SYN packet into the kernel under test. And then on the next line, we have an outgoing SYN-ACK packet, where Packetdrill will sniff for the next packet coming out of that system under test and verify that it looks like a correct SYN-ACK. Here we're using the ... ellipsis for the contents of the options, because in this case, in this test, we don't really care what the outbound options are in this case, and it can vary depending on the machine, and the interface. You might have different MTUs, you might have different receive buffers that allow different window scaling values, etc. So then finally we inject the third packet, which is the ACK completing the three-way handshake. We accept the connection. And then we use a Python snippet here to assert that the congestion window is the default value that we expect, which is 10 these days and has been for the past decade and a half or so. And then we write some data into the socket under test. Then we assert that the TCP stack sends that out on the wire. And then we do something a little more interesting here, where we inject 3 duplicate acknowledgements with some SAC blocks there. And that is basically a hint to the TCP sender that probably that first packet with sequence numbers 1 through 1001, probably that was lost. So that causes the TCP sender to enter fast retransmit. So that means we're expecting it to retransmit that first packet. And then we send an ACK to basically simulate a case where indeed that retransmit plugged a hole. And then we make an assertion about cubic making the correct congestion window reduction in the face of that packet loss. Cubic is supposed to be reducing its CWIN by 30%, so we assert that it does, and Packetdrill will check that for us. So that's a sort of typical Packetdrill test case, just to give you a sense of what these look like and what they can do. So Packetdrill actually can run a test script like that in 2 different modes, which I sort of alluded to earlier, but let's talk about that in a little more detail. So the first mode in which you can run a test is local mode, and that's basically running on a single machine using a ton virtual network device, and that's basically targeted to make testing faster and easier. And that can test the sockets layer, the layer 4 transport layer, can test layer 3 behavior, IPv4 or v6. And basically it's a pretty simple scenario where you have a single Packetdrill test process that reads the script. It has an interpreter loop that runs the system calls, shell commands, and it's going to inject packets via that ton virtual network device. And then it's going to sniff the packets coming out of that virtual network device and make sure they happen at the right time and have the right contents. So the second way you can run a test is remote mode, where it's doing testing over a real physical NIC on a real physical LAN. And in that case, you're using 2 machines. And this allows you to test not just layer 4 and layer 3 and the sockets layer, but also layer 2 and layer 1, including the driver, any offload mechanisms, the NIC itself, your LAN. And the way this works is the first machine runs a client Packetdrill process that's running on top of the kernel under test, and that's making the system calls, checking their results, and it's running shell commands that change the kernel's state. And then you have a second machine that's a sort of server Packetdrill process running on a remote machine, and that is injecting packets over the real local area network, and then sniffing packets coming out of the kernel under test and verifying those packets, their contents and their timing. So let's draw some pictures to see what this looks like. Well, first, actually, let's just show you the syntax for this. So local mode is very simple. You're running a Packetdrill process as root on a single machine. All you need to provide is the path name to the scripts you want to execute. So this is what it looks like, Packetdrill and then the script, as you would expect. And then how does that work? So as we mentioned, basically in local mode, we've got a single Packetdrill process running on top of the kernel under test. And the way this works is that you've got a sort of traditional interpreter loop inside Packetdrill that reads and parses the script and then executes all of the events in that script. For shell commands, it uses the system library call to call out to bash to run whatever commands you give it. For system calls, it makes those system calls directly into the kernel. For packets, it either injects a packet into the ton driver if it's an incoming packet. If it's an outgoing packet, it sniffs for a packet and then verifies it. And then, of course, those system calls are down into the sockets layer, which will call down through the network stack to emit those packets out of the ton driver. And then when the networking stack has events or data to report back to Packetdrill, those, of course, will come back up through the networking stack. So that's kind of as you would expect. It's basically a traditional black box testing model where the thing that's under test is the kernel networking stack. So for remote mode, that's pretty similar, except obviously you need to specify one more piece of information, which is the DNS name or IP address of that remote server machine that's going to be injecting and sniffing packets. So it looks like this. You start your wire server, and then you start your client process by pointing it at the wire server, telling it how to connect to that server, and then, of course, giving it the path names of the scripts to run. So how does that work? So basically, as you see, it's very similar to the previous diagram, except that we've sort of split off the part of the functionality that is interpreting events that are packets, and we're now running those in a remote interpreter loop in the Packetdrill server process on the remote machine. And what happens is when you start up the Packetdrill on the client machine, it starts up a TCP control connection to the server process, and they coordinate using that TCP control connection to coordinate the execution of the events in the script, so that when there are shell commands or system calls, those happen on the client side. When there are packet events on the server side, it either injects a packet down through the NIC and across the LAN to the NIC of the system under test, or it sniffs for a packet sent by the kernel under test through its NIC over the LAN into the NIC of the server machine that's doing the validation of the timing and contents of those packets. So that's how remote mode works. So an interesting aspect of this is that you can potentially reuse scripts and run them in either local or remote mode. The same test can basically be executed in both modes, as long as the network stack behavior in both cases, as asserted or checked by the test, is the same. And notably here, of course, different devices can have different MTUs, which causes different MSS values. And so you can get different test behavior unless you're careful. And one way to deal with this is that you can often work around with some aspects of this by, for example, using the ... feature for outgoing TCP options. You can say, I don't care about the outgoing TCP options in the SYN-ACK or SYN because I don't care what the MTU is of this device, or I don't care what the receive window is in this case. And you can sort of make a given test work in either mode by strategically eliding your assertions here. In the example script that I provided a few minutes ago, that one actually can run in both local and remote mode because it's using that trick. All right, so that's sort of a lightning overview of Packetdrill, and now let's sort of move on to the basics of using Packetdrill on a daily basis. So one thing to mention is that there are actually a couple different varieties of Packetdrill floating around at this point. There's sort of different forks. There's the original Packetdrill written by our team at Google, which is out there on GitHub at this location. There's also a version of Packetdrill that is heavily used by the BSD community at that URL there that supports UDP Lite and SCTP and is targeted at the FreeBSD and macOS community. There's also, interestingly, a version of Packetdrill for Quick that was implemented at Apple and published a few years ago. But as far as I know, that hasn't been open sourced yet. If you're interested, I can point you at the team that did that, or you can check out the paper. So that was mainly a question of the Packetdrill tool. Then there's a question in the Packetdrill test suites. So there are, for Linux, there are a couple different test suites that are mainly relevant here. So recently, you may have seen in the past year, about 72 Packetdrill tests were added to the Linux source tree. And we hope to get more and more tests into that test suite for folks who want to do continuous testing of mainline Linux. And there are some tests on GitHub in that same Packetdrill GitHub repo. And some of you can see it's a larger number, so some of those tests haven't been ported over yet. We're working on that. And then we have a considerably larger set of about 1,100 internal tests that we use internally for our team for testing of Google's production Linux kernel. And we've sort of accumulated tests over the years. And as time permits, we're trying to gradually open source those to mainline Linux, and also to gradually move tests from GitHub to mainline Linux. And just to get a flavor of the kinds of things that are tested, these are the subdirectories inside the TCP subdirectory in the GitHub repo. So that'll give you kind of a flavor of the kinds of things for which there are tests out there. So just a quick word for reference for people who want to play with this or use it for testing. The way you can download and build it, the version that we have on GitHub, is that you can obviously first install the dependencies that you'll need. Then you can use Git to download the source. And then it's sort of a typical tool. You can just use configure and make, and it should build for you. And if it doesn't, email us on the Packetdrill mailing list, and we'll fix the issue. There is a, on the GitHub repo, we have a test suite that I just mentioned. And the easiest way to run that full test suite is to use the run all helper script by Willem. And you can sort of just cd into the appropriate directory, and then just sudo so that you're running as root, and then run the run all script and tell it what directory you want it to run. And if you do TCP, it'll recursively run all of the TCP tests. And conveniently, the run all script will handle the tricks you need to run each script in all three address family modes. And here's just a quick explanation of the command line options that we're suggesting here. Basically, I recommend often using S to serialize things. By default, it'll run things in parallel, but that can cause timing flakes because of the tax on the CPU. Although if you have enough CPUs, it can work. Onto the question of Packetdrill errors and how to handle those. Because a fair amount of your time, since this is a test tool, a fair amount of the time is spent in sort of edit test cycles, or you might see a report for a Packetdrill test that's failing in some automated test runs, and you want to dive in and figure out what's going on. So there are a couple different types of common errors that Packetdrill will flag for you. Obviously, there are syntax errors and semantic errors. For example, you might specify a packet that just doesn't make semantic sense. More interestingly, there are system call errors where either the return values, return data, or completion time didn't match what the script expected. Or analogously for packets, obviously the content or timing may not match the script expectations, or you might time out waiting for an outbound packet and no packet comes at all. Obviously, shell commands can fail, and that can be useful. For example, if you want to check SNMP counters, you can just do a grep to pull out the nstat counters and then you can verify that they're the value you want, and make sure that the bash command fails if it's not what you wanted, and then that can help you validate the SNMP counter values. Similarly, obviously, the Python scripts can fail if there's an assertion failure or something like that, in which case Packetdrill will show you the Python stack trace and show you exactly where things failed. So just a quick little bit of documentation on how exactly to interpret Packetdrill test failures. They're kind of like you would expect from your experience with a C compiler, say, where when there's an error, the error message will have the file name, in this case, the file name of the script, and then a colon, and then the line number within that file, and then the details for the error. So for example, if you have a line in your script where you're specifying you're expecting an outgoing packet that looks like that, you might get an error message that looks like the following, where it tells you that the sequence number field was not what it expected. It expected 3001, but actually it got 1. And so then it gives you a summary of the script packet that you expected, and then the one that it actually saw. Are you guys able to see the cursor if I move that around? Yeah, okay, great. And so in terms of how to interpret this error, obviously that's telling you that this test.pkt file on line 21, you expected a packet that looked like this. Actually, it looked like that. So that's the sort of the most common error that you'll see with Packetdrill. So how do you troubleshoot these kinds of test failures? So obviously, as with anything, it's useful to rerun and acquire more data as you're rerunning. There are sort of 3 levels of detail that can often be useful. One, the sort of highest level is to just rerun with -- verbose, which will print out information about system calls and packets, show all of the TCP info values and things like that. They're available to Python. If you need more details, the gory details, you can run with -- debug. Usually that's just useful if you're modifying Packetdrill itself and something's going wrong. The most useful approach in general, I find, is to basically go back to the roots of Packetdrill, which are focused around strace and TCP dump, and actually literally use strace and TCP dump on the Packetdrill execution itself. So here are some example kinds of command lines you might use to run TCP dump in the background, dumping all the traffic. Port 8080 is the default port, so that'll allow you to see the traffic, whether it's on a ton device or a real device. And then you can run strace and look at the system calls that Packetdrill is running on your behalf. That generally is the most useful approach in my experience. So a little high-level advice about running Packetdrill tests. Obviously, the standard advice for writing unit tests applies, but in particular, it's really great to add comments for future readers and maintainers because they will be debugging any failures of this test that you're writing. It's super useful at the top of the file to have a 1 or 2 line comment explaining what you're trying to test and verify in this test case. And then I find it's also good to have comments down in the body of the test to sort of explain the key moments of both the input, where often you're injecting a particular kind of packet, and then also then explaining the expected result from the network stack under test, where you want to say, well, this is basically what we expect the kernel to do, and this is why, so that if there's someone else who's looking at a failure, they can read this sort of explanation of the intent of what you're trying to test and what is supposed to happen. That can really help things. It's great to keep tests small and focused, just like any unit test. It's great to make the test names clearly convey exactly what you're testing in this particular scenario, so that if somebody is seeing an automated test fail, they'll typically see the name of that test fail. So if the name of that test conveys the functionality that's being tested, that can really quickly tell the developer, what might be broken in this particular internal kernel release. And obviously that eases review, maintenance, and interpreting and root causing failures. we find that it's good in tests to avoid making assertions or checks outside the particular narrow focus of a test. So for example, we like to say that only tests that are specifically testing receive window behavior should check outgoing receive window values. And that can really minimize or focus the amount of toil or churn that is required when network stack behavior changes. So for example, if you change the way that you are translating the amount of receive buffer into the amount of receive window, you don't want to go through all 1,000 tests. You want to just go through the 10 or 15 tests that you have that are specifically targeting the verification of receive window behavior and change those. And then finally, we advise making the dependencies that a test might have, making those minimal and making those explicit. So you want to avoid assuming specific configurations like receive buffer sizes or congestion control algorithms, because obviously those are going to vary. Each Linux distribution or each site might have different receive buffer configurations, different congestion control algorithms. So if a test depends on one of those, then it should really set or check that value explicitly. And we give an example with our example script where it was setting that the congestion control algorithm should be cubic. So there are some interesting best practices around handling configurations and network namespaces. So over the years, we've found that it's useful to sort of have a single script to set the config values that you expect in your test suite. And then second, we've found that it's valuable to run Packetdrill tests inside a network namespace. That way, most of the sysctls that you might change or are going to be per network namespace. So if you change one of them, that change will only affect your test. It won't affect the rest of the system. And that can be really useful because if you do change a global configuration parameter for the machine, and then your test doesn't clean that up for whatever reason, that can cause some really mysterious or hard to debug test failures. So you really want to avoid that. And then finally, we've also found it's useful to have explicit tests for the actual sysctl parameter values that you care about. And because actually there can be bugs inside the kernel in the code that is actually initializing the sysctl parameters for a network namespace. And we've actually seen that in at least one case where you can have a conflict resolution bug that will initialize your network namespaces in a way that you don't expect. And so if you're encountering that bug in combination with approach number one, you can have tests that don't catch that issue. So we do suggest that you have a specific test that tests all of the sysctl values that you care about. So ways to integrate Packetdrill into your workflow. Obviously, it can be useful if you're trying to reproduce bugs or replay traces. If you have a theory about what might be going wrong from a bug report, you can test out your theory. And some people find it useful for documenting in a git commit message what is the buggy scenario that's being fixed, or what is the functionality of the feature that's being added. We do find it very useful to use Packetdrill in the following three ways. First is we find it really useful for creating unit tests during network stack development. So whether you're fixing a bug, adding a new feature, it can be useful to make sure that your feature is really behaving exactly as you expect on a packet by packet level or system call by system call level. We also find it really useful to run full regression test suites before sending a change for review to one of your peers, and certainly before merging it into the source tree. And finally, we find it useful to have automated test spinners that are continuously doing regression tests, running the whole test suite. And we also find it useful to do that for both regular SMP builds and also debug and address sanitizer builds. If you are interested, we are delighted to have contributions by the open source community and happy to review and merge those. If we posted some guidelines for the recipe we're hoping for on the GitHub site. Mainly, we just hope that you join the Packetdrill mailing list. Can certify that you can sign off that this code is okay to submit. We like folks to use the check patch script from the Linux source tree to check the style of the C code. We suggest that style for the commit first line summaries. And then you're welcome to post patches either as a GitHub pull request or using old-fashioned emails to the mailing list, just like with the Netdev list. So I'll spend a little time with some more advanced tips and tricks and nooks and crannies. So some thoughts on MSS and MTU. This is sort of a key part of making tests work with all address families. With Packetdrill, the default MTU we use is 1500, as you would expect. But if you want a test script to be able to be run without modification for all address families, then obviously you have this issue where the IPv6 headers are 20 bytes bigger than IPv4. So traditionally what we do to make that work is for the IPv6 runs, we just tell Packetdrill, hey, we want our virtual device MTU to be 1520 so that the amount of payload data is the same after we factor in the IPv6 header size difference. And that obviously it's a little bit less realistic, but it seems to work just fine in practice. And test orchestration frameworks like runall.py will typically handle that detail for you. And they'll typically just run all three address families, and you don't really need to worry about that detail. But it's good to know about if you're debugging something. And also for handling different packet sizes and making tests easy to read, we kind of recommend a convention of using an MSS of 1000. That way, the packet math is much easier for folks to write and read. One issue that you generally will run into on a daily basis with a new text especially is some timing flakes, because things can take a few milliseconds longer than you expect sometimes, especially with debug or address sanitizer kernels. So a couple tips on how to deal with that. One, we recommend using relative timestamps when you can, because that avoids failures due to accumulating timing errors from CPU consumption or timers firing later than you expect. We recommend being careful with shell commands, obviously, since those are running external binaries. If that binary happens to not have been used since the machine was booted, obviously the machine might have to read that from disk. Disk seeks can take longer than the 4 millisecond tolerance. So, you got to be careful with those. And so we recommend trying to just use shell commands just in setup and cleanup blocks to deal with that. If you need them in the middle of the script, you just have to be careful and be aware of that. Another thing to be careful with is exponential backoff with retransmission timeouts. Obviously, that means that any noise that you had, say, in an RTT measurement will be magnified as the TCP timer is doubled over time. So you'll want to be careful with that. And sometimes you may want to or need to specify a range for the time at which a timer fires. But that typically handles things just fine. So another trick you can use is defining symbols from the command line. So sometimes you may want to reuse a test script that has slightly different system call inputs that are required on IPv4 and IPv6. And so the way you can do this is you can use a feature it's kind of like the feature where you can define macro symbols on the command line with GCC to handle platform differences. Similarly, with Packetdrill, you can use -D to handle differences between IPv4 and IPv6. So for example, a script can use some generic sort of protocol generic symbols like C-message type receive error here. And then you can see that when runall.py runs an IPv4 test, it will define that to mean the code point that you need for IPv4. when you run with IPv6, it'll define that symbol to me, the code point that you need to make it work with IPv6. So just some quick examples on what you can do with ICMP testing and what that looks like. Mainly that can be useful for testing how TCP and UDP deal with incoming ICMP errors. Say if your packets are too big for the path MTU. And here are some sort of quick examples of what that looks like with IPv4 and IPv6. You can say, I want to send some data, watch it go out on the wire, and then you can inject an ICMP message saying that packet was too big. And then you can assert that TCP immediately retransmits that data. And we actually have some features we haven't upstreamed yet where you can actually assert that the GSO size of those packets was correctly smaller using the smaller MTU. That's something we on our to-do list upstream. But similarly for IPv6, looks very similar, except IPv6 annoyingly renamed these ICMP error codes, but the essence is the same. Packetdrill also allows you to test UDP. Now that might sound a little silly because UDP being so simple, what is there even really to test? But actually there are some useful things you can test. So you can test issues relating to MTU, incoming ICMP errors, make sure the TOS values are correct, things like that. So here's just a quick example of a UDP test program where you can check the MTU, you can send a packet, you can inject an ICMP message saying that packet was too big, and then you can verify that, oh, we got an error code because of that ICMP message, but then actually we can continue to read packets, things like that. Packetdrill can also test encapsulation of some common kinds of encap, IPv4, IPv6, GRE, MPLS. And the way you can specify those is to sort of specify the encapsulation header and then a colon, and then either the next encapsulation header, with an arbitrary chain of encapsulations if you want, and then finally your layer 4 header here at the end. And then this provides some example syntax for various kinds of encapsulation. And obviously, Packetdrill can both inject encapsulated packets and then verify that the encapsulated packets coming out of a kernel under test are correct. Another thing that can be useful to test is ECN, or explicit congestion notification. So Packetdrill allows specifying the 2-bit ECN field both for injected and sniffed packets. And this is useful for the 3 main kinds of ECN out there in the world. So there's classic ECN, which is RFC 3168. There's DC-TCP style, and there's L4S style. And they all use the same 2-bit field and the same for bit values that are described here. And Packetdrill just allows you to use one of those tokens to sort of indicate what is the ECN value that it should inject or expect when sniffing. You can also make specifications for other important IP header fields. There's what various people might call TOS or QoS or DSCP or traffic class. You can specify those using TOS, and Packetdrill uses that same syntax for all for both IPv4 and IPv6. You can make specifications about the flow label field in IPv6 packets. So there are a number of recent innovations deployed for Linux TCP, and for which there are SIGCOMM publications talking about ways that you can improve performance and reliability by having TCP do PLB load balancing, where it can use congestion signals like ECN to indicate that the current path seems congested. Why don't we change the flow label of the packets? And then if you're in a data center, which is using the flow label for hashing, for picking switch ports, then you might actually be able to repath your packets so that they're taking a path that's less congested, so that you can fully utilize the available bandwidth in a data center network with multiple paths. Similarly, if you're in a data center environment using flow labels to pick switch ports, you can also use a feature called protective reroute, which basically means when there's a retransmission timeout, change the flow label. Hopefully that'll change your path to a path that's going over links that all work and routers that all work. And so those can be very useful. We use those in production to good effect. You can read the SICOM papers for more details. And finally, you can also specify the TTL for incoming or outgoing packets. Again, we use the term TTL, even though, again, IPv6 annoyingly calls it something different. All right, so wrapping up here. If you want more information about Packetdrill, there's the README on the GitHub page. There's a Usenix annual technical conference paper from back in 2013. There's a Usenix login article giving a sort of pros tutorial style overview. And there's also the Packetdrill mailing list on Google Groups. You're welcome to subscribe and ask any questions you might have or post patches. There are a couple of things that I can foresee in the future might be really useful. And if there are folks who are interested and have time to contribute something like this, that's great. The two specific things that I sometimes think about are first, I think it would be great to have a simple little sort of black box recorder option that will, if a test fails, dump a sort of time-stamped log of all of the packets and system calls, when they happened, what happened. And that could really help speed troubleshooting, especially if you've got tests that are failing in automated test runs and you just quickly want to see what went wrong and you don't want to get your tests set up to reproduce that in your own environment. So a second feature that is would be trickier to implement, but could have a really high payoff would be an integration with user mode Linux and time travel mode. And time travel mode allows a Linux, user mode Linux process to basically advance its virtual notion of time as fast as events are scheduled rather than at a wall clock rate. And this could really speed up testing by running a test suite in a sort of simulated time, kind of like a discrete event simulator like NS3, instead of having to sort of go through the slow process of booting a kernel on a machine and then running these tests in wall clock time. So in conclusion, our team finds Packetdrill useful. We hope other folks find it useful to be useful too. And we're excited about the fact that some Packetdrill tests are now in mainline Linux. And we encourage folks who are interested to contribute features or fixes for the tool, or contribute new tests to the test suite for Linux, or help port existing tests into mainline Linux. All of those contributions are welcome. And thank you very much. I'm happy to take questions now or in the chat after the session. Thanks a lot.
So question about the language. So you showed a bunch of examples how you specify the packets, which is, I'm assuming it's some kind of minimal specification language. Is that, you didn't show anything about L2 really, I think. So I was wondering how easy that is to extend or to use other protocols maybe. Specifically now I'm thinking about Wi-Fi, but maybe someone else, the MP, TCP people, other people would find it useful to extend. So I'm wondering how that would work.
Right. I suspect it would be straightforward. It was straightforward to add the encapsulation support. So I imagine adding the support for specifying L2 headers would be kind of similar. So yeah, we're open to that if folks would find that useful. Yeah.
Yeah. Oh, it's just because we just mentioned MPTCP. In fact, there is already a fork of Packetdrill for MPTCP. It's just that the code is not really nice, written by a student, but I will talk too much about that. But there is something that already exists and can be used if you want to use it with MPTCP.
Yeah, thank you very much for mentioning that. I should have mentioned that. Sorry for leaving that out.
So I noticed that you have a postscript basically to clean up and reset device settings. So one of the things we're doing at Meta is whenever we change any device setting in a test, we just reset the entire device by doing a PCI remove and rescan. So why don't you do something like that, which guarantees that the device is fully reset?
So you're welcome to do that if you want. So most of the things that the existing suite of Packetdrill tests are changing are software changes inside the networking stack. And so the device reset, I don't think would help in those cases. But yeah, folks are welcome to send patches or if you have suggestions. Yeah.
Thanks.
I have a question. So in terms of the remote setup, when you're working with another device, where is it that the packet inspection would actually be happening at? Is it at the sender or the receiver?
The packet inspection is happening at the receiver on the remote machine, so that basically it verifies that the packet really did go out through the physical NIC over the local area network and into the NIC of the remote machine, so that you know that the packet that you're seeing is really the packet that was on the wire.
And it's only at one point, you can't do it at both? It's like I'm thinking of, for example, something like TSO testing, where it might be interesting to say, okay, we want to see a 4K packet on this side and MSS size packets on the other side. Would there be any option for setting something like that up, or is that be, you know, patches requested type thing?
I think that would be a patches requested type thing. Yeah, if you wanna do that, that sounds totally feasible. It would just take some, you know, adding some plumbing to do the checks on both sides. Yeah.
Okay.
Did you find some interesting bugs in the mainline kernel using this? And can you share some examples maybe?
So in the interest of time, I'll just point you to the Packetdrill paper from 2013. That actually gives some examples of about half a dozen bugs maybe. I mean, honestly, we do a ton of bug fixing and feature additions within our team for TCP. And so I think we find, at least I personally find, that Packetdrill allows you to catch most of the bugs while you're doing your own individual development. And so, you know, you can catch many, many bugs just as you would imagine with unit tests as you're developing your own code. And so the nice thing is that you can catch those bugs early enough that actually they don't become painful memories that you remember years later. So I don't have any examples that come to mind from recent years, because usually we catch bugs before they're merged into our particular TCP stack. I'm trying to think of things that I'm sure as soon as we're done, I'm sure I'll think of examples. But you can go back to the Usenix paper from 2013, and there are concrete examples with commit SHA-1s if you want to look at the bugs.
If there are no more questions, we'll let Neal go. Thanks, Neal.
Great. Thank you.
Appreciate it.